All right, this video is basically going to cover steam tables. So by the end of this, you should know how to use them. So before that, let's kind of go into the concept of what a steam table is doing. So I guess as a baseline, let's assume you have a rock. Let's just say that's a rock. And you put heat into the rock. Put heat into the rock. What'll happen to the rock's temperature? Well, it'll probably go up. T will go up. So if we plot this, T versus Q, as Q increases, T should increase. So it'll be like a line. I don't know what the slope will be. It might be like that or like that, but it'll be a line. Now, what if we have a phase change material? Well, rock is technically a phase change material because it can melt and turn into lava, but at practical temperatures, it won't do that. But what if we have like water? In water, if you heat it up enough, it'll phase change into steam. And if you cool it down enough, it'll phase change into ice. So what would this TQ plot look like for water? So starts off as ice, and as ice, you could think of it as a rock. So you've got the ice rock. That's supposed to be an E for ice. Okay, so as ice, you can put heat into it and it'll heat up normally. But then, when it transitions to water, if you put in heat, it won't heat up. Instead, it'll melt. And that's because melting absorbs heat on its own. So what'll happen is it'll melt. And it won't change temperatures. So that'll happen at a constant temperature. Ice, melt. Okay, now you have water. So again, assuming it stays water, which it will for a while, if you put in more heat, it'll heat up at a constant temperature, or it'll heat up at a rate. I'm gonna assume it's steeper. Chances are like this slope and this slope won't be the same. So I'm trying to draw it so it doesn't look like they are the same. Okay. Cool. So now we have water. All right, and then the water will turn into just steam. And again, that process of boiling is going to be flat. It's going to be at a constant temperature. And then you can heat up the steam all the way to infinity. Well, it'll turn into plasma at a certain temperature, and that's another phase change, but we don't worry about that. I'm gonna change it. I wanna. Okay, there you go. Cool. Cool beans. So, quick overview, you start out with ice, and if you put in heat to that, the temperature will increase. But once it hits the melting temperature, if you put in heat, the temperature won't change. The only thing that'll happen is more of the ice will melt. And then once all of the ice is water, then you put in heat and it heats up, the temperature goes up. But once it hits the boiling temperature, it won't heat up temperature anymore. All the heat will be absorbed by the water and turn it into steam. The phase change process will absorb that heat. And then for steam, put in heat and it increases the temperature. Okay. Typically, in thermodynamics, we only really care about this region. So I'm going to redraw it with just that region. Actually, there's one more thing we could do. So if we're at atmospheric pressure, so if we're at, what is it, 14 point something, 14.7 psi, I'm going to use bar because the table that we're going to use uses bar. 1 bar is basically 1 ATM. So if we're at 1 bar, what would these temperatures be? Well, water melts at 0 Celsius and it boils at 100 Celsius under normal atmospheric pressure. But we'll get back to pressure later. Okay, so drawing the relevant parts. Cool. That is this part. Okay, so what is the effect of pressure on this? So if you got, as we mentioned, if you have water at 1 bar, these will be the temperatures at which melting and boiling happens. If the pressure is higher, what ends up happening is everything moves up a bit. I want to draw this well. I'm going to say your pressure is way higher. Normal P, high pressure, and then we'll do a low pressure. Low pressure. Cool. So if you draw dots, well, if you connect these dots, you'll get a parabola sort of thing. And I think I have a picture of this. No thanks. Yep, here you go. So you can see this is a temperature versus, well, it's T versus S, but it's the same idea. You can see the different pressures. You can see the bell shape. Where's one with a bell? Yeah, here we go. P low, P high. There. So that's literally it. That's what that chart is telling you. Okay. So let's glance at the steam tables. So the whole idea of the steam tables is based on 2 inputs. Let's start out by saying temperature and pressure. You can know everything else about the fluid. You can know the density, you can know the enthalpy. Gas constant is R, the entropy, and the, what is this one? The inverse of is a specific volume. So it is meters cubed over kilogram. Yeah, it's the opposite of density. All right, so the whole idea is if you know any 2 of these, you can find where you are on the tables and you can get everything else. So let's say you know the specific volume and you know the entropy. You can find where you are on any of these tables and you can know the temperature, you can know the pressure, you can know the density, you can know enthalpy, you can know whatever you want. That is basically the idea. By the way, here it says 10 to the 3. It's actually 10 to the negative 3, even though they don't put it. And the way I know that is because density, it's 999, so it's basically 1,000. And specific volume is 1 over density. So this has to be 10 to the negative 3. Okay. So let's do an example. Let's do a normal example. So let's say we're at 1 bar, so atmospheric pressure. One bar and a temperature of, what should we go with? 150 Fahrenheit. Let's do Celsius. What's a good temperature? Let's say 50 Celsius. So we know that we're in the water region. Cool. Which table would that be to begin with? So there's the saturation table. You can tell it's a saturation table because it's got subscript of G. This should be a subscript of F, but it looks like L. You can tell it's a saturation table because it's got those subscripts. And saturation table is for a mixture, and the mixture is the boiling region. So it means you're somewhere in there. And then there's also, this is still saturation. Here we go. Compressed water and superheated steam. So these tables would be if you're in the water region or the steam region. So there's two types of tables. There's saturation, which is for mixtures, for boiling. And then the rest of the tables are for if you're water or steam. All right, so we picked 1 bar, 50 Celsius. Right away, we know we're gonna be in the water tables, not in the mixture tables. So let's see if we could even find it in the mixture tables. No, we cannot. And the reason why, so right here is 50C. So this first column is temperature. 50 Celsius has pressure. Pressure is second column? Yeah, pressure is the second column. Wish I could draw on this page. Of 0.12344 bar. Which is, I might as well just keep this line here and make it another color. Let's make it green. So under our pressure, under our 1 bar pressure, we know boiling happens at 100C. So what would have to happen for boiling, for the boiling temperature to be at 50 Celsius? Well, we would have to be at a lower pressure. And that's what this is saying. So this is saying if your boiling is happening at 50 Celsius, your pressure is 1.2344. So we're not there. Right away, you can tell that we're not in the boiling, in the mixture region. So we shouldn't be using these tables. Here we go. All right, we said 1 bar. These are 0.1 bar, 0.1 bar, 0.5 bar, 1 bar, and 50 Celsius. 50 Celsius right there. So we know the specific volume, first column, is 1.01212, density 988.03, enthalpy U, and entropy. There you go. That's how we use a table to find that data point. Now, let's assume we're at, let's say, 10 bar. And 300 Celsius. 300 Celsius. Okay. So what I did here is I increased the pressure. So we go from normal pressure to higher pressure. So we're somewhere up there. And I also increased the temperature. So we know by default that the new boiling temperature is going to be higher because I said 10 bar instead of 1 bar. So we know it's going to be higher than 100 Celsius. We don't know how much higher. And I also made the temperature higher. So we really don't know whether this temperature means that we're at the boiling point, or in the steam region or the water region. We don't know where. So we have to use the tables to find out. 10 bar, 300 Celsius. Okay. Step 1, we can very easily find out what region we're in by starting off and looking at the saturation table. So where is 300 Celsius? Temperature is the first column. 300 Celsius, and pressure is the second column. If we're boiling at 300 Celsius, that means that our pressure has to be 85.8 bar. We were only at 10 bar. So for this specific curve, what it'll look like, if we're at 300 Celsius, this has to be line for, what was it, 83? 85.8. So if we're at 300 Celsius, we would have to be at the 85.8 bar. We know that our pressure is below that. So a lower pressure means lower temperature. So I think this means my brain's just did a blank. So yeah, if we're at 300 Celsius, but we're only at 10 bar, I think that means I have to think about it for a couple more minutes. There's a very easy way to answer it. I can't think of it right now. But we for sure know that we're not on the steam tables. We're on the other set of tables. So let's go to them. I said 10 bar, so let's go to the 10 bar table. 1 bar, 2 bar, 5 bar, 10 bar. And we're at 300 Celsius, 10 bar, 300 Celsius. Okay, so specific volume of 257, density of 3.87, H of 3050.6, etc. All right, there we go. Those are our state properties. Now, dang it. We're at 10 bar, 300 Celsius. I guess an easier-ish way to do it would be to go the other way. So what boiling temperature corresponds with 10 bar? Here we go. 180 Celsius corresponds with the 10 bar boiling temperature. Let me draw that out better. So at 10 bar, we know this temperature is 180 Celsius. And this is the plot that we use because we're at 10 bar. We're not at a higher level. We're not at a lower level. We're at this one because this is 10 bar. And this temperature is 180 Celsius. So since we're above that, 300 Celsius, we know we're superheated steam. So this case is superheated steam. And we found it. We found it on here. 10 bar. (300°C). Cool. Okay. Now let's do a mixture region. So let's say I'm going to cheat and look at the tables to get inspiration. Let's say we're at let's just keep it simple. Let's say we're at 15 Celsius. So right here. And our RH is 500. What is the quality of our steam? So quality, I didn't really explain that. Quality is what percent you are along this boiling curve. So if you're at this point, you're at 0% quality. If you're at this point, you're at 100% quality. So it's basically what percent of your water is water and what percent of it is steam. And if you're like over here, you're maybe 70%. If you're in the middle, you're 50% quality. If you're over here, 20% quality, which would mean 20% of your water has turned into steam. Okay. So what was my example? Temperature equals 15 Celsius, H equals 500. So 15 Celsius, H is fourth and fifth column, 62.92 and 2528. All right, so HF, the first one, I know it looks like L, but it's F, is 62.92. And HG is 2528.0. So what do these mean? These mean if you're at a quality of 0%, so if you are all the way on the left side, you're right here, quality at 0%, use HF. If you're on the right side, use HG. If your quality is 100%, use HG. If you're somewhere in the middle, make a line equation and use that to interpolate. So if our H is 500, what quality are we at? So 500 equal 62.92. So I'm just making the equation of a line. And it starts at, so x-axis would be quality. It's from 0 to 100%. Y-axis would be H. So at 0% quality, we're at 62. And at 100% quality, we're at 2528.2. I thought it was 0.0. 0.0. Okay, so if our quality is 500, probably be closer to 0% than we are to 100%. So that's a good check. But let's actually do the math. Plus quality times HG minus HF for the slope. Okay, let's do the math. $500 minus 62.92 is 437. 437 equals quality times 2528 minus 62.92, 2465. So that means our quality is 437 divided by 2465, 0.18. Which is closer to 0% than 100%, so that meets our check. Cool, so if we were given this temperature and that H, we could tell you that we're at this quality. And you do the exact same line, like interpolation thing. If you're looking for the entropy, if you're looking for a specific volume, or I guess density. Exact same approach. Okay. I think that's about it for the steam tables. So I explained these plots. I went over a couple examples of how to use the steam tables for all the regions. I went over an example of how to find which region you're in if you're given the properties to identify the state. And I went over a quality example. I think there was one other thing. Oh, yeah. Okay, constant CP assumption. That was way down here. All right, at the bottom of this website, they have a bunch of other tables. They have viscosity, they have thermal conductivity, which is heat transfer, viscosity is fluids, specific heat capacity. So what is this? So this is CP. So if you've used Q equals mCp delta T, that works and it's valid as long as the temperature range, as long as the delta T is not too extreme. So if the delta T is, I think, what was the rule of thumb? Less than 300 Celsius. So if the change in temperature was less than 300 Celsius, you could roughly assume constant CP and get a pretty accurate answer. But if you have a huge change in temperature, like say 1000 Celsius, CP changes based on temperature. It's a function of temperature. And if your delta T changes by too much, assuming a constant, CP won't get you an accurate answer. So for example, let's say we're at 0 Celsius, 1 bar. So we would be at this 4.228 number. And we go to 300 Celsius. Dang, that's actually a huge drop. 2.013 bar. So maybe the 300 Celsius isn't a very good rule at all. All right, let's look. Then we're at 300 Celsius versus 600 Celsius. I guess that's fine. It goes from 2.013 to 2.203, all the way down here. So I guess don't start at the temperature of 0 Celsius. As long as you start somewhere in the mid-range, you'll be fine. Yeah. But if you want to properly do, like if you're writing code to do this mCp delta T, you would do Q equals M times the sum times the sum of CPT. So you would go, let's say you start at 300 Celsius and your Q is, I don't know, Q is like 2000 kilojoules, probably. Your Q is like 2000 kilojoules. You start at 300 Celsius. What would your final temperature be. So it would be MCP delta T, but you would go 1 degree by by a time. So you would say, all right, to go from 300 to 301. Maybe you can't do that small of increments. You would have to go by 10 degrees because it goes from 300 to 310. So from 300 to 310, you would use a CP of 2.013, and now you're at 310 degrees. And then to go from 310 to 320, you would do 2.018, and then 3 all the way down until your total summation gets up to the 2000 kilojoules. So that's like the proper way to do MCP delta T. But you could assume a constant CP if your delta temperatures are relatively close, which is what you do in like all of thermo, unless you're coding it, unless you're hard coding it. But yeah, I think that is literally it for steam tables. This website I found to be the best one because it has all of them in metric units. I think that's the right thing, which is the better unit. And it's got all the tables in one place, so you're chilling. Cool beans.